everyone, welcome back. Today we have William who will be telling us about the first taste of elliptic genera.
Hello everybody. I'm really scared for this talk because this is like the first time I've had to learn something new for a seminar since the atom spectral sequence talks like 2 years ago. So it's still a work in progress. I'm still slowly, incrementally working our way through like the source that I'm using. It's Hirzebruch, which is always great. Hirzebruch, Berger, and Jung. Um, yeah, sort of trying to bridge what was happening in the 1950s, 60s that I already knew about with all of this elliptic stuff that started injecting into algebraic topology in the 80s, and trying to understand myself what is elliptic cohomology and how to do things with it, because I eventually want to talk about the Witten genus, which I think is not actually elliptic, which is strange, but it is expressed in terms of these parameters for elliptic things, and these parameters turn out to be modular forms, and I have no idea what any of that is about, so I'd like to learn it. So we're starting at the basics. We're working our way through the basics, and what's the point? Yeah, so I'll do a recap of what we did last time, because if you're anything like me, you'll have to see all this stuff like over and over and over again before it starts to sink in. So the really key fact that we're using, which is a big sort of sledgehammer result by Tom, was that the oriented Bordism ring is actually polynomial in generators in degrees divisible by 4. Complex projective spaces in particular. So these are the really important spaces for us to consider. So in particular, since this is a polynomial ring, we typically define a genus is a ring homomorphism So this is, I think, Hirzebruch maybe came up with this definition. There's lots of things that arise naturally in this way, such as the signature of an oriented manifold is a ring homomorphism defined on this rationalized oriented Bordism ring to some rational algebra R. And I think people want that to be a principal ideal domain. We're not going to be so technical about these types of assumptions. I think they probably are important. So in particular, since this is a polynomial ring, a genus is determined by its value on the generators. So if you want to distinguish two genera, it's enough to just test them on complex projective spaces and see if they agree or not. That might not be enough to tell you what's value on every single manifold, but we're going to see, well, actually last time we saw that, in fact, that is enough information. And I'll recap that calculation right now. So I'll note that determined by the set of all values on complex projective spaces. So last time we had a mechanism for constructing these. We start with an even power series with leading coefficient 1. And everything we're doing is just going to be like base field Q, or R, I guess. Yeah, so if you wanted to have values in R, you would take even power series over R. I think today I'm probably going to mostly just focus on R equals the rational numbers, though. But later on, we'll do more general stuff. So how do we make a genus out of this? What was the idea? So given M, dimension 4n, with Pontryagin class, so remember this is P of Tm, tangent bundle. There's one Pontryagin class in each degree divisible by 4. So there's n plus 1 of them, including the 0th one, which is just always equal to 1. So this is the Pontryagin class where, as always, you define the ith Pontryagin class of a vector bundle to be -1 to the I times the second Chern class of the complexified vector bundle. So this is something that's typical for characteristic classes. This is just what you do. There's reasons, but I've explained them all in previous talks. So given this Pontryagin class, formally factor, so using splitting principle, we can formally factor our tangent bundle into a sum of oriented line bundles, and this has a corresponding factorization of our Pontryagin class into so-called Pontryagin roots. So x1 squared, and we typically write these to be squares of variables because of the way that we're defining our Pontryagin class in terms of Chern classes. So using the splitting principle, I thought about this on the way over. You're taking your thing and expressing it as a sum of line bundles, right? So, so for each line bundle, there's only one Pontryagin class. And this oriented line bundle, since SO2 is also the same as U1, this is also canonically a complex line bundle. So in order to calculate the Pontryagin class of your real vector bundle, your real line bundle, you're actually forgetting a complex structure and then complexifying it again. And by doing this, what you get is the original complex line bundle, but L plus L dual. I should be writing this out, but I'm just recapping. And so because we have L plus L dual, you apply your Chern class to that, get the second Chern class, you do a calculation, and you find out that your Pontryagin class is just 1 plus the first Chern class squared. So this is why I'm writing these things squared, because this is like a first Chern class. So xi are the Chern roots, essentially, of the appropriate bundle. That's why we're taking them squared. It's kind of an important part of the theory. I just wanted to point that out. So if we do this formal factorization, then just, the theory of symmetric polynomials then says that the ith Pontryagin class is going to be the ith elementary symmetric polynomial. I'm going to use k to distinguish from this I in these Pontryagin roots. So we had the whole formalism that I went over with the Pontryagin classes you can think of as elementary symmetric polynomials in these formal roots that we can take in a splitting space.
Question.
Yes?
Do you happen to know why it's called a genus?
It's like Greek for type or something like that. It's just a name, one of those names. Probably trying to generalize the A hat genus. So we'll see that more in this talk. Okay, so given such a formal factorization into these things, we can sort of automatically construct something that's multiplicative by taking Q of x1 up to Q of xn. And we remember that Q is defined to be even at the get-go, so it's automatically a function of the xi squareds, but we can just plug them in for xi. This is symmetric in the xi's. And so this should become a huge sum in terms of elementary symmetric polynomials. And I wrote this sum in terms of homogeneous degrees. So let's take a sum over homogeneous degrees. You're going to get a weird polynomial. You're going to get some polynomial in the elementary symmetric polynomials. Sorry, this is going to be an I, and this is only going up to pi. And then you run out of Pontryagin classes. So you're going to keep adding forever ki p1 up to pn, and then it's going to be zeros because you just ran out of variables. But this part doesn't depend on n. So the idea is that if you want to compute the nth coefficient, you just take enough variables in order to reach that point. And if you had taken more variables, everything up to that point would still be the same. So this kind of stabilizes. To give a characteristic class which I'm going to call K, and it lives in the cohomology of BSO, so the stable special orthogonal group with rational coefficients, and I really mean like the product of all of the cohomology classes. So I'll put 2 stars there to emphasize the fact that this is really like a power series in the Pontryagin classes. So I say that this as a ring is generated by the Pontryagin classes, but in fact as a polynomial ring. Okay? So we get some power series in these Pontryagin classes with the property that because we've defined it in terms of the splitting principle, it's also multiplicative. So K of V O plus W, or even external product VW, this is equal to k of v times k of w. Oof, what is this? Okay. So yes, it's important this construction gives us something multiplicative because we're trying to mimic a ring homomorphism. We need it to be multiplicative in order to actually define a genus. And so the fact that, I proved last time, so phi q m, you can try to define a genus by saying, all right, take this characteristic class, k, plug in the tangent bundle of m, and then evaluate it on the fundamental class of m, which corresponds to the orientation. So a choice of orientation gives us a class m in the homology h4n of m, a priori with integer coefficients, but it's rational as well. So we make this definition, and this is a genus. So this is what I'm recapping, is that we had a mechanism for starting with an even power series, and we make a genus out of it by forming a multiplicative characteristic class. Okay, point. That was the first stage of the last talk. The next stage was, well, what happens, can we go backwards? So given such a genus, right, we know that it's determined by its values on the CPNs. Is there a way to determine the values of this genus on the CPNs without actually going through the whole rigmarole of defining this characteristic class, calculating the Pontryagin numbers, and sort of like brute force plugging them in? Is there something more clever you can do? And that was the second part of the talk. Okay. Do you have questions? Yeah, I'll write that better. This is homology in degree 4n, the same dimension, like the real dimension of the manifold. Yeah. Do you have your eraser? Yeah, because like this eraser doesn't make it that much better either. Not always, anyway. Yeah. Thanks. Okay, this gives me a chance to think about how to segue into the next part.
Writing bigger is always better.
Okay. Try writing bigger.
That's fine.
Okay. So this is one way. So now there's a brilliant computation trick to go the other way. So the first thing we do, well, what are the Pontryagin classes of CPN? So we're still doing recap. If you take the tangent bundle of CPN, and if you add to it, consider it as a complex vector bundle, a trivial complex line bundle, you go and you check Milnor-Stasheff, and the standard argument which shows that this is the dual of the tautological line bundle to the power of n plus 1. So gamma is the tautological line bundle, where over every point in CPN, the complex vector space living over that point is just the space that the point represents. That's what makes it tautological. And the gamma bar was its dual. And so the first Chern class of this dual bundle is the class in second cohomology with z coefficients. That is a Kronecker dual to downstairs right, the 2 skeleton defines for you a second homology class, and this U upstairs is the Kronecker dual to this, and it's also, what's a better way of saying it? Yeah, it's the cohomology class that evaluates this thing to 1. Okay, and so if we then go and we take the Chern class of our tangent bundle, so this is a stable characteristic class. And it's also a multiplicative characteristic class. So you get n copies of it. So we just get 1 plus, and I said u to the n plus 1. So this is, in general, what is the total Chern class of the complex complex projective space. Okay, so from here, how can we figure out how to get the total Pontryagin class? Yeah. This is the trivial complex vector bundle of rank 1.
Okay.
Yeah.
And what was the Kronecker dual again?
The Kronecker dual is, so, right, you remember from your universal coefficient theorem.
Right.
So you have a map like this, H, N, X to R. And so, yeah, if you have a homology class here, you're picking a cohomology class, which is basically the class representing, wait, no, what am I saying? I'm saying something dumb. Yeah, hold on. Okay, so the point is, yeah, universal coefficients theorem. In this particular case, the error term is 0, so you get an isomorphism here. And since this is all like finite dimensional, right, this isomorphism between, yeah, Hn and H lower n dual. So if you choose a basis of this thing, for example, like this is a basis element for this group. So choosing a basis of your vector space or Z module, if you have a free one, that basis induces the Kronecker dual in the dual of that Z module. It's the one which takes, you know what I mean? You've seen this before, I'm sure. So if A up to AN in say a Z module A is a basis. So witnessing that it's isomorphic to Z to the N, then we have a Kronecker dual. Which looks like A1 star up to AN star for A upper star, where AI takes an AJ and it gives you delta IJ. That's why it's the Kronecker dual, because Kronecker came up with it. So this is like the standard thing that you see in linear algebra all the time, or at least if you take like the P-math quantum information linear algebra class. Okay, yeah, good question. That's all I meant by that. Yeah, I'm going to erase this because that somehow didn't work. Okay. Okay, so now let's find the Pontryagin classes. And so if we want to find the Pontryagin class for TCPN, right, so remember what we're doing is we first have to forget about the complex structure. Okay, this is annoying, but remember we had this annoying sign in the Pontryagin class. So if we define P bar to be equal to the alternating sum of Pontryagin classes, then your P bar of something is actually equal to the Chern class of that thing complexified. So what is this? All right. Where am I at here? And so what does this tell us? Well, not much yet, but if we stabilize it once with a complex thing, so real dimension 2, so this is going to be like a plus C, and this is going to be like a, split this up, plus it's going to be like this. And then we're going to get the usual splitting. This is gamma bar n plus 1 plus gamma n plus 1. So this is 1 plus u to the n plus 1, and then 1 minus u to the n plus 1, because dualizing changes the sign on the odd Chern classes. And so this is equal to 1 plus u squared, 1 minus u squared to the n plus 1. But this is P bar. So to get P, it turns out you just change a plus to a minus. So this is the Pontryagin class, total Pontryagin class for complex projective space CPN. And so we're going to use the fact, so remember when I said, okay, we're going to compute a genus by taking some power series and making some multiplicative thing out of a formal factorization of the Pontryagin class. But here, in fact, we don't even need a formal factorization. We already have a factorization of the Pontryagin class. Even though this bundle doesn't split, the Pontryagin class still splits. And in fact, that's enough to just automatically read off what the multiplicative characteristic class should be for this space. So the outcome of this calculation, which was a little like whiz-bang, but here's the outcome for us at this moment. So our genus that we define with a power series Q, if we want to read it on CPN, like we said, so you're supposed to take, right, n different copies or however many different copies of Q according to your formal factorization and plug in those different variables. Here, all those variables are the same. We're actually just taking QU to the power of n plus 1 and then evaluating it on our fundamental class CPN. So half the time this is going to be, well, this class is going to be 0 half the time, and half the other time we don't know what's going to happen yet, but we're still just keeping a general n just to keep, just so we don't have to deal with like parity and stuff like that. Okay, so what's the point is that we saw last time that to do this calculation, this is the coefficient of, what is it? U to the n in QU n plus 1. And what we did was some residue theory stuff. So res of dot, dot, dot. And the point was, in the point of writing it like an integral, is we could do a clever change of variables. And it's not even that clever. So the change of variables, we essentially just said, okay, let's let Q of x, or I guess we're talking about U here. Oh dear. Oh dear. Oh, this stuff? Yeah. Oh dear. Oh no. Okay. I'll try not to make mistakes from now on. How's that? I think that's more legible. This could probably be better as well. Thank you. Okay, so we basically just renamed some things. It turns out in the course of this calculation, since we needed to divide by a big power of u, it turned out that the denominator of this ratio is actually the important part. And then we did a change of variables by letting, what is it? Let's say v equals f of u. And we have inverse function g, so that u equals g of v. And what we ended up getting was the coefficient of v to the n in g prime v. Okay, so big deal, what's the point? On this side of the trick, we had something that depends on n, right? So this is like, okay, we still have this specific situation. We're plugging in this specific n. We have to do this specific calculation. And once we go through this change of variable, this clever change of variables, we find out that this is really, there's one power series g prime that doesn't depend on n at all. And we're just trying to find the coefficient in g prime. So our g prime, in fact, as a power series, it just, well, I'll write it out like this. It just allows us to read off the values of our genus on, which ones are these? These are going to be, yeah, squares. We can, our coefficients of this power series are exactly the genus evaluated on our complex projective spaces, right? So in principle, we had to do some, characteristic class calculation for a general space, for this special space, our characteristic class calculation simplified so much that we can just create one power series that answers for all of them at the same time. So this power series is what we call the generating series. For our genus phi q. And what this is telling us as well is that if we already know what our genus is as a ring homomorphism, we can just apply it to every complex projective space to get a power series called G prime of V, and then just try to step backwards. Integrate it to get an F, or sorry, integrate it to get a G, invert it to get an F, and then just flip it over, multiply by the same variable to get our Q back. And this is the mechanism by which we take a genus and produce a Q so that, right, phi equals phi q. So this is how we got to last time. This was the big theorem of Hirzebruch, is in fact that all of these genera here are exactly the same as even power series with leading term 1. It's the same set of things. And so now given that, we can give an example or recap the example from last time. So phi equals sigma, the signature of an oriented manifold. Remember, this was defined in terms of its intersection form. And we see that for all n, the intersection form of, what do we have? CP2n is just, okay, well, the middle dimension cohomology for this space is a copy of Z. It's rank 1. So it's only determined by a number. The whole thing's a polynomial ring. If you take the thing in middle degree, square it, you get the generator in the top degree. So this intersection form is really just the number 1. So the signature of all of these manifolds is equal to 1. Therefore, our G prime of y is nothing more than 1 plus y squared plus, sorry, this should be a 4. Sure, it should be a squared. Y squared, y4. Did I do something? Did I write the wrong thing? Ah, okay. Yeah, I did write the right thing. Just pretend you can tell that's a 2, which is really just 1 over 1 minus y squared. Daniel saw immediately, of course, that if you integrate this, you get arctangent. Of course, everybody, every kindergarten student knows that this is arctangent in the Persian school of mathematics and physics Olympiads. And then if you invert this, of course, you just get tangent, right? Tangent. And then your characteristic series, of course, is just x over f of x is x over tangent x. Okay? It's one of the best. So from this characteristic series, now you can just explicitly compute Hirzebruch's L's polynomials. Like you're already done the hard part. The hard part was just a calculus trick, and now you can just compute. So the Taylor series for this, I'll just write down the results. So you just go and plug it into Wolfram alpha, gives you a Taylor series. You take n different variables, and you collect them all together in terms of elementary symmetric polynomials. And I think I did an example of this last time. I actually explicitly computed it. This time I'll just write it down. These are the L polynomials. So if you have an 8-dimensional manifold and you know its Pontryagin classes, you plug them into this, and whatever number you get, that's the signature. So this is a great tool for taking something that you know already in a topological form, in something that has nothing to do with characteristic classes, and you just produce a characteristic class that spits out the values of this ring homomorphism.
I understand that the power series shows up, but it's kind of surprising.
It is surprising, and this is kind of where like the elliptic stuff is sort of underlying this whole story in a way that I don't really understand. And I'm working incrementally through this whole picture to try to understand the elliptic stuff. But it is like the tan H is like something elliptic is happening here.
It's something kind of important like this. Okay.
Yeah.
It's not just like coincidence.
Yeah, it somehow is just not a coincidence in this case. It's strange that like topologists kind of cared so much about the signature in the first, like maybe it's coincidental that like this special elliptic thingy is actually something that topologists sort of care about. And it's also maybe not a coincidence because the second example is the A hat genus, which is something that like physicists and geometers care about quite a lot. And I'm mixing my terminology here. Yes. Okay, sorry about that. So the A hat genus, right? And you'll see people will say that this is the index of the Dirac operator. I'm putting in quotes so I don't have to explain it. On a spin manifold. And the next thing, also please don't ask me to explain it, but the Atiyah-Singer index formula in cohomology tells us that the characteristic series for this genus is given by this. Qx equals x over 2 sinh x over 2. It just is. It just came out like that. So this is the A hat genus. This is also like an elliptic thing in a way that I don't really understand yet. And so given this, you just blast it out as a power series, and you can compute the characteristic class A hat is just given by this. Right, like etc. This is something that computers were invented for us to do. I think it was more just like, why does it appear?
Why? Well, sorry, and I was going to ask about like what's the sense of elliptic we're using here? Like, of course, like there's a topological sense, but like.
I think there's actually only one sense. I think elliptic is like one of these words that seems like an overloaded term, but in fact, every time you see it, it's the same form. It's the same thing. It's in the sense of like, you have a lattice on the complex plane and you have a function as elliptic if it's doubly periodic. Somewhere underneath all of this, that's happening. And I'm very slowly trying to figure out how by just, again, working gradually through Hirzebruch. So here's our Q, right? Okay, so we're given this A hat. This mechanism, right, this is just index of Dirac. Suppose I don't know anything about differential geometry, right? Stretch your imagination. And suppose that this isn't something that I personally want to figure out. And suppose someone gives me this. Well, now I can turn the crank and figure out through Hirzebruch's formalism what is the value of the A hat genus on every complex projective space. So our f of x in this thing is going to be a 2 sinh x over 2. And so g of y, our inverse, is going to be 2 arc sinh of y over 2. And then if we simply take the derivative of this, like of course Daniel's going to tell me exactly what this is, it's 2 divided by the square root of 4 plus y squared. Sorry, 5 to the 4. Sorry, I think this should be squared. Maybe not. I think g is supposed to be, let's see, yeah, g is odd, g prime is supposed to be even, so it should be a y to the 4 because it's being a square root. I think this is a 4 or a 2. You can't read my writing anyway because of the stuff on the board, so it's something. But whatever it was, the power, the Taylor expansion for this does look like as follows. So you just do calculus, etc. And now we can read off. This is the A hat genus of CP2. It's minus 1 over 8. This is the A hat genus of CP4. This is the A hat genus of CP6, right? So by this formalism, we can compute an arbitrary genus's value on our complex projective spaces by just doing this. So I'm really trying to hammer that home. this is still actually a recap from last time. So this is a good point to stop because this is the end of the recap. And, we're at a good time. So if people would like to ask questions, this is an ideal time to do it, because what we're about to do next is try to apply the same idea to the next more difficult space, which is quaternionic projective space. So like understanding this part of the story is going to help the rest of the talk not be so boring. No, everyone understands. Okay, I will take a drink. Okay, lots of fun power series, lots of neat tricks. You kind of have to be good at calculus to do this, and I'm not, so it's a struggle. So the next thing,
It's a square.
it is a square. Very strange.
Because usually the derivatives of functions are quite involved in stuff.
That's okay. Odd. I guess there's cancellation or something. Okay, thanks for that. So part 2 of the talk, I guess, which is the new stuff. What about quaternionic projective space? Since this has a really simple cohomology, which I'll just write out for you, it looks almost exactly the same as complex. It's just spaced out a little bit more. So this is still a polynomial ring on one variable in degree 4, truncated at that. So the highest group is in degree 4v, and then everything above that is 0. So it looks very much the same as CPN, except it's spaced a little differently. And it turns out it's a little harder to compute its stuff. Because it's complex, well, I guess I won't say why, but it just is. So here's the coolest thing that I've seen all week. So we want to compute the Pontryagin classes of this manifold. So the one thing that we do know the Pontryagin classes of is complex projective space. So we're going to try to relate these things together and see if we can just pull this data that we have back to here, maybe with some correction terms. So how can we relate these two together? So this is great. So by definition, what is quaternionic projective space? So we can express this as a quotient of compact manifolds. So you start by going to n plus 1 dimensional quaternionic space. The real dimension of this is 4n plus 4, and the unit sphere of this is real dimension 4n plus 3. This has an action by the group of units of the quaternions, which is S3. And the quotient, by definition, this is HPN. And so this is a S3 bundle. Principal S3 bundle, S3 is a group. This is also, let's see, how do I want to write this? Maybe parallel. Let's make a second copy over here. This is an odd dimensional sphere. You use the same type of thing to make complex projective spaces. So this quaternionic vector space of dimension n plus 1, if you forget part of the structure and remember that it's complex, this has dimension 2n plus 2, right? And so this is defining for us, by taking the quotient by S1, the complex projective space of dimension 2n plus 1. And you get a map going like this. And the fiber of this map, S1, is an S3 mod S1, which is your classic block sphere, CP1. So in fact, yes, good question, yes.
So is it I have time to ask?
Probably not. Yes, please ask.
Can you explain the first 4 plus 3 again? Actually,
This one?
yeah.
This is just because this is the unit sphere in this projective space. or this quaternion vector space, n plus 1?
Yes.
Because this
yes,
has dim
yes,
4
yes,
n
yes.
plus 4.
Yeah.
Yes. 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 Good question. Yeah. So we get this sort of formidable fiber bundle. And if you look real close at this, what is this actually doing on homogeneous coordinates? Let me see. You have z1, z2. How many homogeneous coordinates we have? I think it's 2n plus 2. What you're actually doing is just making quaternionic numbers out of them. Right?
Yeah.
And this goes up to z2n plus 1 plus j z. I can't possibly write any bigger than this. You know what I mean? And if you in particular look at the fiber over 1 with a bunch of zeros, like, take that as your canonical base point, and the fiber over this is obviously just all z1, z2 that live in the same I orbit. So this is clear that the fiber over this point actually is the inclusion of the usual CP1, like in the standard way that it's included into CPN. Okay, so in this fiber bundle, I'll call this map iota. Iota is actually the inclusion of the two skeleton. So we know fully geometrically what this map does. We already know what that does. It's an isomorphism on degree 2 cohomology. And it pulls the tautological line bundle over CP1, or over CPN, back to the tautological line bundle over CP1.
That's the inclusion, right? The very bottom thing that you have.
This one, no, this one's kappa. So this is the fiber over this point.
And can you explain the bottom set again? The one you have the equality at the bottom.
Yeah, so I'm thinking about what is this map doing? It's just taking consecutive variables and adding them together with a j on the second one. And I'm thinking about, okay, what are all of these that map to this? So what is this map? This is the equivalence class where we act on 1 by all of S3. So it's the S3 orbit of 1. Or what am I saying? No, hold on. So what are all the pairs Z1, Z2, which are in the same SZ orbit? Sorry, S3 orbit. How am I saying this? Aha, any Z1 and Z2, their Z1 plus JZ2 is in the same S3 orbit as 1. No matter what Z1, Z2 you take here, their thing here is going to be equivalent to 1 under the action of S3. Because of the quaternions, it's a group. S3 is a group. So if at least one of these is not 0, then added together it's going to be non-zero. So you can invert whatever that is to bring you to 1. So yeah, the fiber over this point is just all possible where at least one of them is not 0, and that is CP1. Those are the homogeneous coordinates for CP1, like the usual one. So this actually really is just the usual inclusion of CP1 into the larger projective space. Yeah. Okay, so like I said, we can deduce from that. So iota star is an iso on H star for star less than or equal to 2. Because it's the inclusion of the two skeleton into this thing that has nice spacing. What about kappa? So this is a claim for you. This is an exercise. Kappa star is an isomorphism when so I'm going to say in degree for R, and I'm just going to say that it's immediate from Serre spectral sequence. So if you were there for Serre spectral sequence, you draw the spectral sequence, you know that there's no possible differentials. Every differential is going to be 0 if you just like draw out what are the degrees of these spaces. So the E2 page is already the E infinity page. You look and you see there's no possible extension problems. And so you already get that the E2, as an algebra, a spectral sequence of algebras, on the E2 page you just have the tensor product fact, I will just write it out like this. On the E2 page, you have the tensor product of these two. And the E infinity page, or the thing that you're converging to with no extension problem, is this. So in fact, this bundle constructs this ring as a tensor product of these two. Very neat, very neat. So in particular, if you keep track of generators of all of these things, so I think I chose to use V for here. So I want this to be an N, and I want to make it more clear that this is a 1. And this is going to be V to the N plus 1. This is, I chose a U to go here. And this is going to be, sorry, no, a mu. Yes. And then this is modulo mu squared. And then this is an N. And this is a U, modulo U to the N plus 1. And this data says that iota star takes U to mu, and kappa star takes V to U squared, I think. I just want to double check. Yeah, that's all pointing the right way. Yes?
The degree of the cohomology is asterisk for any degree of the cohomology, right?
This is like as a tensor product of two graded rings. So like on the left-hand side, something in degree k is something, is basically like in bi degree that add up to k. So like the H4 here would be like H40, H40, H31, H22, blah, blah, blah. But like there's not really that much happening. So like it's just, if there's something non-zero here, it actually just comes from like one copy of Z each on the left-hand side.
Sure, but what is the superscript of the cohomology?
Oh, those are as asterisks. Yeah. Guess not super clear. Okay. So we're still computing this. Okay. So given that, now we actually do some work. So now notice the tangent bundle choose a metric, I should say. So if we choose a metric, we can take the tangent bundle of the total space and decompose it into horizontal vectors and vertical vectors. And so I write like this, TCP2n, sorry, 2n plus 1. I should mention that after. Okay, this tangent bundle decomposes, like I said, into the horizontal vectors, which is kappa star of the tangent bundle of HPN, which is the thing that we want to understand, plus the kernel of the differential of K, of kappa. So these are the vertical tangent vectors. Everything that that lie essentially over a point. And I'm going to call this T, just so I don't have to write that out all the time. So now, applying Pontryagin classes to both sides, it's a multiplicative characteristic class. On this end, we know that this is what? 1 plus u squared to the 2n plus 2. We computed that. On the right-hand side, we get the Pontryagin, well, we get, by naturality, kappa star of the Pontryagin class of the thing that we want. So this is the quantity we need to compute. This is something we know. And then this is something else that we need to figure out. P of t. This is not very easy to read. Okay. So if we can figure this out, then the idea is we can just invert it, use the fact that kappa is an isomorphism on degrees divisible by 4, and then just translate that formula down to quaternionic projective space. So how do we figure out what this is? I'll just follow my notes because I didn't review this. So note the following. So if we take T, our vertical tangent bundle, which is a rank 2 bundle, and we restrict it to our fiber, we exactly get the tangent bundle of that fiber. Okay? So in particular, if we're computing the first Chern class, where this restriction map is really just iota star, this is T1 TCPN which is 2 mu, because this is the 2-sphere. And you can just compute by the formula that we had before that you should get a 2 there. So it follows then, in particular, that if we take P1 of t, right, this is negative C2 of the realification tensored with C, right? Same game as always. This is just T plus T bar. Whitney product formula. T is a line bundle, so it doesn't have any Chern classes above degree 1. So we just get C1T times C1T bar. Odd Chern class, so taking the dual adds an extra negative. This is simply C1T squared, which is equal to 4 mu squared. So we have our first Pontryagin of t. It's 4 mu squared. And now we can just isolate for the thing we want and push it downstairs. And I think this was Hirzebruch's original argument for how to compute this Pontryagin class as well. So therefore, we can isolate is equal to the Pontryagin class we computed that I just erased, all that computation for CPN, times the inverse of this other thing. Something's fishy here. This should be a u. When you pull it back, you get a mu. But if I'm not pulling it back, I get a u. Yeah. So here's our kappa. And so since kappa is an isomorphism in degrees divisible by 4, and we know how these classes correspond, we get this. Okay, here's our Pontryagin class. Boom. Okay, good. Excellent. Yes. Next. Okay, so just as like a minor extension of this argument, now if K is any multiplicative characteristic class, coming from one of these even power series in the usual way, then we can mimic the same argument. I'll skip it because of like time, and I think like I'm belaboring these fine details a little bit much at this point. So mimic the same argument to get what? T, so K applied to this complex projective space should just be our Q U to the 2n plus 2. And you should be able to compute that K of T is equal to Q of 2U and put it all together to get that K of, right, whatever this characteristic class is, multiplicative characteristic class for our quaternionic projective space is actually just going to give us, I'm going to write it, Q V 2n plus 2 times Q 2V inverse. So it's a similar principle to what we had before. We already essentially have a factorization in terms of Pontryagin roots, but you can't just get it directly from this formula. I don't think you have to go back up to this splitting, do the magic up there, and then just pull everything back downstairs to get this very convenient formula for any multiplicative characteristic class. So now that we have this formula, we can say, all right, we're off to the races. We can actually compute the value of our genus on HPN by doing the appropriate residue integral with this expression.
Something similar with OPN for n less than 3.
Can you rephrase that question so it doesn't like sound like a crazy person is saying it? Okay. So you're asking if we can do the same thing for OP2, is what? Yeah. Let me think. I'm not quite sure because you have to deal with S7.
Yeah, exactly.
Yeah. So this is kind of like what I was saying. Like the issue with like acting by something that isn't a group is that the orbits aren't equivalence classes anymore. So taking a quotient set doesn't make as much sense. So if you could introduce like some more technology, maybe something stacky, I don't know, that can deal with actions by monoids like that, then you might be able to do something. Yeah, we got to do it. Okay. Okay. So good question. Good segue. So remember that big long recap I was talking about. In order to compute the genus on CPNs, we did some weird residue trick. And so we're going to try to see, given that formula that I just derived way over there, can we do a similar kind of residue trick to get a power series whose coefficients just tell us what is the genus on HPN? And the answer is actually yes. It's just a little bit more complicated. So can we do similar residue trick? So this is basically just writing. So as always, I'm going to be a little bit, going to recap what are all of our things. We have a Q. And we've decided we should write it like this in order to facilitate the residue trick. We have a variable y that we've named f of x, and we invert f by a function named g. And then, of course, this lets us say that dx is g prime y dy. And moreover, this is going to be relevant, f prime of x should be 1 over g prime of y. Even though those are different variables, they make sense because y is actually just f of x. This is just the chain rule. Okay, so given this, let's compute. So what we want to do, so phi of HPN, by that formula over there, this is just what happens when you take the coefficient of x to the 2n in this series. Q of 2x inverse. And so we write this as a residue. So first you divide by x to the 2n. Sorry, x to the 2n plus 1 times 2x inverse dx. And now we start plugging things in to try to turn this into our integral over y. Let's do that, okay? So first of all, our qx, right, since this is an x over f of x, I'm missing a certain number. There should be one more. So most of the x's cancel with this one. And we get what? I guess I'll just write it. Yeah, I'll just write it out instead of trying to skip steps. So this is going to be, yeah. So we're really doing this. I have to write bigger. And this is going to be an x to the 2n plus 2 over fx to the 2n plus 2. So I'm just taking qx and unloading what that means, times f of 2x over 2x dx. Now let's start canceling out. All of the x's go away. We get the residue of f of 2x. Let's just replace this with the y. Let's replace this with the g prime dy. And we have something that almost looks good, except we have this f of 2x. We'd like to write that in terms of things that we like. What are things that we like? Well, if something like f of x is actually y, that y would cancel out with one of these y's and it would be very nice. Our f prime of x is actually 1 over g prime y. It would cancel with this g prime y, which would be very nice. And I missed a factor of 2. And so this is kind of the motivation for the following trick. Oh, you want to know what the trick is?
Yeah.
Oh, you want to know? Okay. No, I'm going to say that I'm going to pick a function that we wish f of 2x was. Notice that they have the same leading term. Right. And then point out, oh, well, there's an even power series with leading term 1 that acts as an error between those two functions. So we'd like something like fx f prime x for cancellation purposes. I believe this is the motivation. You'd like stuff to cancel, and this is the thing that you want to do those cancellations. So you notice f of 2x and 2fx f prime x. Why is this? Okay, why that? I forgot to mention over here, of course, this is an even power series starting with 1. Even. It follows that f of x is an odd power series starting with x. So f prime of x is an even power series starting with 1. So their product is an odd power series starting with x. And so if you multiply by 2, these both have leading term 2. And they're both odd. So I'll leave this as an exercise to you. If I proved it, so can you. It's just calculus, and I'm bad at calculus, so I believe in you. So exercise, there exists an even power series. And this is called h tilde of x. And it starts with 1, such that f of 2x is equal to the thing that we want times this error term. No, it's just like power series. Multiply them together, you get a series of equations, and you can inductively show that they have a unique solution. You don't have to do anything hard.
That's a method for solving these.
Yeah, okay. That's also a method for solving DEs, sure. It's the hands-on William Gollinger method. So, okay, and for convenience, let's let hy be h tilde applied to g of y, so that we can write our integral thusly. One moment. Oh, I forgot to mention. I'll mention later. I hope I remember later. So then we get that residue, right? So the thing that we're trying to compute, which is the genus of HBN, and we've reduced it to a residue calculation so far. I'll just write it down again so that it's fresh in our minds. 2y to the 2n plus 2 g prime y dy. And so we just came up with this h, which lets us do this. So this is going to be a 2fx f prime x h y g prime y dx, sorry, dy, over 2 da 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 da. So like I said, f of x is a y, f prime x is a 1 over g prime y. This actually turns into g prime, sorry, h of y over y to the 2n plus 1 dy, which is the coefficient of y to the 2n in hy. So it actually does work. We do get another one of these power series, which a very, very strange way of doing so. But I'll write up what is the theorem that we've just discovered by doing this. So theorem, or lemma, yeah, I don't know. I think Hirzebruch calls it a lemma. We just showed if hy is such that, I'm going to make sure that I get the form of this correct, or I'll look like a fool. And we want this to be an even power series with leading term 1. If h is such that plugging f into it gives this ratio, then, in fact, this is the power series that we want. Hold on. Yeah, this is right. right? This is the power series that spits out quaternionic projective spaces. If we can find something that implements this strange thing. So this sort of formula, I've seen, it gets the name duplication formula. So from what I understand, this is when notions of things like formal group laws start to enter the picture. This is where notions of things like elliptic curves start to enter the picture, because there's this idea of a completion of an elliptic curve giving you a formal group. And so the definition now happens. Do I not define that yet? Hold on. I should define this somewhere. I guess I don't define it yet. Let's look at examples of this, and then we'll write down our definition. Okay, I've got 58. Okay, I don't think I'll take that many. Good. So we don't need to rush, but I'll still have plenty of time at the end. Okay, so this is sort of blah, blah, abstract mumbo jumbo. Let's look at some actual examples to see what we should expect for this H. So let's look at our familiar examples of the L-genus and the A-hat genus. Or rather, what if we formally design our H? What if we just declare all of these to be 0? What if we consider the case where H is just constantly the formal power series 1, so that the F that we're dealing with in our genus actually takes this convenient form? So this is a nice functional equation. What kinds of functions satisfy these types of equations? Things like sine of alpha x over alpha satisfies this by the double angle formula. So does, what's it called? Sinh alpha x over alpha. And we saw that our sinh, our 2 sinh, how do I say this? We saw if we have our f for our thing, f of x equals 2 sinh of x over 2. So here our alpha is 1 over 2. This gives the A-hat genus. So since by assumption H is just 1, all of the quaternionic projective spaces have to have vanishing genus. So what this is telling us, by doing some incredible calculation, I don't even have to know anything about the A-hat genus, spin geometry, or whatever. I just know that all of these are 0 in positive degrees. So that's something that just happens. Doesn't just happen. It doesn't just happen. There's reasons, and I spelled them all out. But it's sort of how, that's incredible, you know? We just do some calculations with some formal power series, and other than computing Pontryagin classes, I mean, we do have to compute Pontryagin classes, but we don't have to know the explicit form of the characteristic class so that we can plug them all in. It's more like we need to, once we know our expression for the Pontryagin class has some really convenient factorization, then our bundle is what's the word I'm looking for? Amenable. Then the bundle is amenable for our treatment of this thing in terms of the splitting principle. Take your characteristic class, take your Pontryagin class, split it up into these characteristic series, and then combine everything back together. If the formula for our Pontryagin class is really convenient, like this thing I just erased, then it's possible to do these sort of simple integral calculations instead of combinatorial characteristic class calculations. So that's what makes this kind of interesting. Okay, second example then. It's going to be across the room. Maybe I can do it off the top of my head. L class. So in this case, yeah, I'll just write it down. So L class, remember we had f of x is just tanh. So maybe I'll save you the trouble. So tanh, maybe you know, has a nice half angle formula. How does this go again? You go tanh x. Do you remember, Daniel? What's the double angle formula for hyperbolic tangent? Sorry, I don't remember. So you get 2 tanh over 1 plus tanh squared, which looks nothing like this form that we want our h to have. Let's do some massaging to it. We're going to multiply top and bottom by 1 minus tanh squared. Do I really want a 2 there? Yes. Okay. 1 plus minus tanh to the 4x, where this is just the derivative of tanh. So if we compare this to our duplication formula, wherever that was, yeah, you can leave it as an exercise to write out that the h we get is nothing but 1 over 1 minus y to the 4. So if you take your f of 2x and you divide out by the thing that you wish it was, whatever's left is our h of f of x. So that's just if we call y f of x, then we just get 1 over 1 minus y to the 4. So here's our h. So what is this as a power series? This is 1 plus y to the 4 plus y to the 8 plus y to the 12. So you'll notice when you compare that to our generating series in general, you're actually missing half of the projective spaces. So the signature of our HPN is 1 if n is even, 0 if n is odd. This is something you could have seen immediately from the intersection form definition, because there is no cohomology in the middle dimension when n is even, or n is odd. But we didn't even have to open up that package at all. We could just do a calculation and find out the signature of every quaternionic projective space. So this form of H, which over here, this H also is of that form. It's just the one where the coefficient of y to the 4 is 0. This form of H is going to be the primary form that we want to consider for our things called elliptic genera. So now we write down a definition. Finally. Okay, and so this is the part where I'm like at the end of the things that I know. I can define what these things are and tell you the important parts of them, but I haven't learned how these pieces work or what is the broader context that makes all of this stuff make sense. But here's the definition. So let phi be a genus. So phi is elliptic if h has the form 1 over 1 minus epsilon y to the 4 for epsilon some rational number. So where the h, I mean, is the power series that kind of implements this duplication formula. And so in particular, if you have an arbitrary elliptic genus, it's automatic. You could just take this and expand it out, that an elliptic genus applied to quaternionic projective space is just going to be epsilon to the k over 2, n over 2 if n is even, and it's going to be 0 if n is odd. So an elliptic genus is structured enough already that we can sort of, by definition, I guess, read off automatically what is its value on the quaternionic projective spaces. Given such a thing, there's still an indeterminism in what is its value on all of the CPNs, right? So quaternionic projective spaces are good to know, but the CPNs are the things that are actually the basis for this ring. So this is only giving us part of the information, and it isn't telling us everything necessarily about what is this elliptic genus. And so I'm going to tell you what comes next. Why are these things important? Why do we care about them? At least from like a computational point of view. But there are deeper reasons for like why they connect to a lot of things. So theorem. This is, you can find it in manifolds and modular forms as an exercise pretty much. Let phi be a genus. And let's let f be the usual thing. Take x over the characteristic series. Let delta be its value on CP2 and epsilon its value on HP2. Then the following are equivalent. So let's see here. So first of all, it's elliptic in the sense of this, which is that ones come first. F of 2x is equal to the thing that we'd like it to be, divided by our error term, 1 minus epsilon of f of x squared. So for this particular epsilon, this has to be true. This, by definition, what makes it elliptic. There's something slightly more general, which is like what happens if you add two distinct variables together. And this is a calculation that I'll need to work out. And if I want to actually present this, you get something like this, a bit of a Leibniz rule, plus, make that more apparent. Oh man, thinking great. Divided by 1 minus the same epsilon. Oh, this should be a 4, sorry. F of y squared. So this is just kind of like an equivalent but slightly more general expression of this. And the third condition is that f satisfies a differential equation that looks like this. 1 minus 2 delta, what is it, a variable above? Oh, sorry, this is f. 2 delta f squared plus epsilon f to the 4. This last thing has the name Jacobi quartic. And this, I think, has possibly the most direct connection to elliptic curves. I think it's something like if you have the general Weierstrass form of an elliptic curve, there's a coordinate transformation that you can make in order to look like the Jacobi quartic x, where if you let y equals f prime, you get this equation, the Jacobi quartic, which is sort of like one of the general equations that describes elliptic curves. So somehow, when we think about, we want a genus whose value on HPN is easy to read off, somehow now we're automatically working like with elliptic curves and elliptic functions, and we have to import stuff that Euler figured out 200 years ago. I'm not even kidding. Some of these books, like I'm reading like these advanced conference proceedings, and it's like this argument is due to Euler. We compute like the formal group law for the Weierstrass elliptic curve or whatever. It's like, oh, cool, man. Good stuff. We're doing real math now. Okay. So this is crazy. So, but the point that I didn't make somehow is that delta and epsilon, where do I make this so that it's like loud enough? So the point is delta and epsilon completely determine. So this is part of the story that I need to uncover why this is true. But if you have an elliptic genus, this is kind of something that makes this so convenient. If you have an elliptic genus, which is something that satisfies any of these three conditions, its value on CP2 and its value on HP2 completely determine the genus. So whereas for an arbitrary genus, we have countably many things we have to determine it on, an elliptic thing is like, okay, you just have to manifolds up to dimension 8, determine the elliptic genus. So from a computability standpoint, like these things are easy to work with. But also from like a theoretical standpoint, since they have such a deep tie to elliptic curves and modular forms, I mean, I guess we also just get to import that entire package of theory. So this is something that I'm in the process of trying to understand. But here's some examples. Let's illustrate for our classic examples one more time. We had the L-genus, of course. Right, so delta is its value on CPN, which we just compute to be 1. And we saw by that earlier example that epsilon signature on HP2, since this is even, this gives us a 1. Good. So there's the L-genus as a genus. is completely determined by the signature of CP2 and the signature of HP2. We have these two formal parameters, delta and epsilon. Our A hat genus, going back to that, we had that power series where we found that the signature of, the A hat genus of CP2 was -1/8. And by our example where we just took our duplication series H to be trivial, just the constant 1, we found that the A hat genus of our HPNs are all 0. So our epsilon is 0. So this is more stuff that I need to understand. This is kind of where the modular forms things come in. So these are cusp points. Cusp points. So the idea is that if you let your delta and epsilon be parameters, you have this entire family of elliptic genera. But somehow these two elliptic genera are singular values. So these are sort of degenerate elliptic genera in a way that I don't really understand yet because I don't understand elliptic functions and things like this. But in some sense, I forget, there's some argument by Witten. He does some clever thing where he does a flow of these elliptic genera, and at one end you get the L-genus, and the other end you get the A hat genus or something like that. Yeah, so that would be cool. That would be cool to look into. I think that's. I like I said, like it's not actually elliptic. I don't know yet. I don't know. I probably shouldn't even be making that claim that the sigma genus isn't elliptic because I don't know enough yet. I'm still very slowly reading through these books by very scary people. And I'm sort of amazed that I understood this much content in the last like 2 weeks. So I have a lot more work to do. And that's, yeah, that's all I had prepared. So thank you for coming out. Awesome. Questions?
Always ask what comes after, but you answered that
Yeah.
in the last 10 minutes of
Yeah.
stuff that you're trying to understand better.
Yeah, good talk structure, huh?
How do you pronounce the alphabet? What's the name again?
Hirzebruch.
Hirzebruch, okay.
Yeah, the Z's are sharp.
I was looking at a copy of it when you mentioned the name of this word. He's very terse.
Mhm.
He's a very terse writer.
Yeah, I think like the first few sections are sort of like, if you have a PhD in algebraic topology, you can understand this. Like you know at least what sources to go and look up these claims in, things like that. I tried to understand this book when I was in grad school, and like I didn't. So this is a big level up.
And this is a math talk. I care about it from the math perspective, math purposes, but is the only reason why physicists would care about it is for theoretical purposes because of Witten?
Oh, I'm not going to pretend to know why physicists care about the things they care about. They don't know why I care about the things that I care about, so it's a fair deal.
Yeah.
And so why do physicists like this? I think it must have probably was Witten. Witten is one of these like bridging guys who just said, oh, this elliptic genus stuff is so great. They appear when I try to do a spinor bundle on the loop space of a spin manifold, even though it's infinite dimensional, and then you get these huge complexes that you have to take the index class of. And he's like, oh, there's these delta and epsilon parameters are modular forms, and then Witten does Witten stuff, and now there's a sigma genus. So
The physicists care instantly about it because Witten.
I think so. I think it might be like entirely Witten's fault that physicists care about this. Yeah.
I mean, he's done this many times before.
Yeah, like this book that you wanted me to read, Elliptic Forms and Modular Curves and Topology. These are like the conference proceedings in the mid-'80s when this stuff was really exploding. And everyone at this conference is like a super goated mathematician, stable homotopy theorist, number theorist, and then Witten is also there telling them about like how physics works and why is this an A hat genus thing. And that helped the mathematicians tremendously as well because it gave them more tools to approach the problem with. And then Hirzebruch's book was something like 10 years after this conference. He decided he just wanted to go through and figure it out himself because he's that kind of a guy. And so he had this like retrospective hindsight. He knew what all the results were and wanted to see if he could kind of piece them together in a narrative that made sense to him. hopefully makes sense to me as well. Yeah. Maybe there will be more talks. Maybe I'll get burned out and give up. I don't know.
That's fair.
Yeah. Sounds good. More questions?
Are you around the fall, or is that like finished like classes?
I will be around. I mean, I just live here,
Okay,
so
yeah.
yeah, I'll be around, but I don't have classes. So in principle, I can give more talks. I shouldn't say that, but it's good. Could happen.
I'll be giving talks as well.
I hope so.
Yeah, I have no classes after.
Yeah. Okay, I guess that's it.
Where can you expect to see the crazy number theory stuff and the TMF stuff?
Oh man, probably like as soon as I start talking about actual elliptic curves and need to start thinking about the moduli stack of elliptic curves. And I'm not sure if schemes come up a lot in the TMF story. Stacks do.
That makes sense.
But yeah, in order to really understand like the interplay between the elliptic curves, like it's sort of, there is a big learning curve. You have to like already know Silverman's book about elliptic curves like inside and out, and I do not.
Mayuko has talks on TMF. I know you don't really watch talks, but I enjoy that.
Maybe, yeah. I wonder, because the only thing I've read about it was this one of these survey texts from like the mid 2000s or something like that, or mid 2010s. I forget. So there's definitely more stuff that's been proven since then.
Yeah, I think Mayuko's talks were approved the past like 5 years.
Mhm.
Yeah, she would be on top of that.
Yes. Another person I definitely have to email.
Yeah.
Yeah.
The elliptic homology on like casual thing that they ran for like she was the one with.
I remember that. Yeah, I was really upset because I wanted to get involved, and then you said, "Oh, well, they don't let like
Yeah.
people into the Perimeter Institute." So I was like, "Oh well, I'll just read them on my own." That's okay.
Nice.
Yeah.
Well,
Thank you.